Good morning, everybody, and welcome to this next CHPC research webinar. Today we have Professor Liliana Mammino that's going to be giving us a presentation. So I'm just going to give you a short bio of her. You guys can read up on her bio from the invite that was sent to you, but just going to highlight a few things that she's done. So Prof Liliana comes from the University of Pisa, and she did a PhD thereafter in Moscow State University in Russia. This was all in theoretical chemistry. She's been a lecturer at the National University of Somalia, the University of Zambia, and the National University of Lesotho. Since '97, she's been part of the University of Venda, where she's developed research capacity in computational chemistry, including supervision of postgraduate students. And she's currently a professor emeritus at the university. She's also got more than 160 publications, 8 books, and she's presented at more than 220 conferences. She's also a national representative of South Africa at the Interdivisional Committee on Green Chemistry for Sustainable Development of IUPAC, and a member of the editorial board of the Journal of Sustainable Chemistry and Chemistry and Chemical Engineering. And she received an award for social logistics by the African Languages Association of Southern Africa in 2016. So with that being said, I'm going to hand you over to Prof Liliana, who's going to give us a presentation on studying a class of related molecules computationally, the case of acylphloroglucinols. I apologize if I messed up that title. Prof, over to you.
Thank you. And first of all, I wish to thank the CHPC and all the colleagues here who have introduced me for giving me this opportunity of presenting part of my work. Well, not only mine, also students, but to say. And I would like, I will say it also at the end, but I would like to thank, since now, the CHPC for providing the facilities to do molecular calculations, because I've been doing molecular calculations for quite a number of years without using the CHPC at the beginning, because it was not yet there. And then some reasons, but it makes such a difference. You really can do research when you have the possibility of having the CHPC. So I would like to thank. Now, why have I chosen this one, these acylphloroglucinols? It is interesting to study classes of related molecules because one can have a lot of fun. But this class is very big, so one can really do lots of things. Sorry, I'm trying to get to the next slide and I'm not managing. Okay. So the advantages of studying a class of related molecules is that one can make comparisons. Comparisons can help understand the features that influence molecular properties and can help us predict the properties of not yet investigated molecule or not yet synthesized molecules. And this is very important, first of all, in drug design, because we need to predict properties before doing calculations on molecules like this. One needed to test and synthesize about 6,000 molecules to get one viable drug. Now people can make calculations on thousands of molecules, but then the actual synthesis is on maybe 80 to 150 molecules. So the cost saving is enormous, because we have to remember that experimental components are always more expensive. And that is the reason that is mentioned in the second point. When we have a lot of data, we can use them as descriptor for QSAR, that is quantitative structure activity relationships, for molecules that have biological activity, and or QSPR, that is quantitative structure properties relationships, for molecules of any other type, for properties in which we are interested. And I think that one of the fields where this will be developed fast, maybe for the structural property relationship, is green chemistry, because they want green chemistry proposes to synthesize more benign molecules, to design. And the only way to design molecules is computationally. First, meaning to make it faster, to make it more efficient. Now, we start by seeing quickly what are acylphloroglucinous. They are structurally derived from phloroglucinol, that is 1,3,5-3-hydroxybenzene, and are characterized by the presence of a RCO group. So phloroglucinol is the small figure in red, and the general structure of acylphloroglucinols is the one in blue. This numbering has been used throughout all the works that we have done. Now, many acylphloroglucinols are of natural origin. They have a variety of biological activities like bactericide, antibiotic, fungicide, antioxidant, anti-malaria, anti-cancer. And recently, some Chinese researchers have found that they can also be used, at least they are active against COVID. So they've been considered as potential health compounds for the development of several drugs, but now there is also this hope for COVID. Now, how has this study gone? Now you see there are some slides with lots of writing, then there will be lots of molecules because it will be faster, I mean, it will be easier. Let's see, what are these? First, we did the conformational study of actual and model molecules of this class, selected in such a way as to have a good range of R chain, the chain in the acyl group, the main substituent. And then very quickly we realized that there are hydrogen bonds, intramolecular hydrogen bonds that are interesting. And we all know that when we consider biologically active molecules, intramolecular hydrogen bonds are important because they can take part in the interactions with proteins or all of the other things that the molecule does for the activity. Then the investigation of solvent effects. It is important to know the properties of a molecule in solution because, above all for biologically active molecules, because they act in the body, meaning they are in a medium. Then study of dimeric and trimeric acylphloroglucinous. There are different classes of molecules. There are, like, the monomeric have the structures that we have already seen, and there can be lots of substituents, different ones, rings, anything. But then there are acylphloroglucinous with 2 units of that type, with 3 units of that type, and even with more units, and they all occur in nature. And the ones with dimeric and trimeric structures have a better activity in most cases. Then we started studying some acylphloroglucinous with specific biological activities. Actually, it started like that. How did I start with these colors of compounds? Because there was a colleague who had discovered one molecule with anti-tuberculosis properties, and he asked me to make the calculations. And starting with that, then it turned out that there were so many other things that one could investigate that we just went on trying and expanding the work. And then a study of supramolecular structures that started as fun. And then it looks like there are cavity-containing structures that might even be interesting. And investigation of correlation effects that was done at a later stage. And the study of the parent compounds and other hydroxybenzenes that we did at the beginning, that I will show you towards the end. Because, okay, computational methods, we started with using PCs, desktop PCs. So we started in a basic way. So Hartree-Fock and MP2 as a single point on Hartree-Fock result, and the DFT and the basis set, we found out that for Hartree-Fock and MP2, the 631 GDP was enough. While for DFT, we needed at least 1+. And when we started using the CHPC, we could do much more. So using MP2 with fully relaxed geometry, using bigger basis sets, but that became a bit of a problem because of the need to be able to compare with the previous ones. And of course, studying much more molecules. And for example, making calculation solution with full optimization. Well, the calculation software was Gaussian, and in different steps, we had the different versions. Now, of course, we are very happily using Gaussian 16 on the CHPC. Visualization, Gauss View, and Chem3D. The molecular structures that I will show are all done with the Chem3D. That is typical for organic chemistry, but that means it is very good for any organic molecule. Now, the objectives of trying with many R chains for the acyl group RCO was that of seeing the influence of the nature and the size of the acyl chain of the R group, and also of the geometries that it can take. Because if we have a methyl, okay, the geometry is very limited, it's just the orientation of the group. But when we start having longer chains, there can be much more options. And then for each of those chains, the substituent in meta to the acyl group was also varied using hydrogen, so no substituent, using a methyl that is a good model for any other type of substituent that will not interact with the phenol OH. Because if there are substituents, say, containing double bonds or containing other oxygen atoms, then we need, the modeling is different because there are additional hydrogen bonds, which I see later. And of course, also actual molecules with the bigger substituents. Now, one thing that is when we have a lot of conformers and we need to compare them, one may have to go every time to the drawings, to the models, the structures, or one can try to find a sort of trick. So we ended up using a letter for each property. In some names, there are 10 letters or more, but say for these, here I showed the simpler ones. And we can see, for example, DR, D means, nobody needs to remember that, but just to show how it works. D means that there is a hydrogen bond, intermolecular hydrogen bond on the right, and the R means that the bottom OH is towards the same side. And then, of course, if that OH goes to the other side, we call W. So DW will be the same hydrogen bond, but that OH turns to the left. Now, if we want to see the effect of the orientation of that OH at the bottom, we just compare a DR and DW with all the values that we may have in a table. We just compare the DR and DW and we have the effect. Say, the hydrogen bond can be on the other side, as we see in the third drawing. So if we have an SR, S is, meaning the system that we used, is to say that the hydrogen bond is on the left and the R has the same meaning for the orientation of the OH at the bottom. So if we compare DR and SR, checking the values, we know that we see the difference or the influence of the hydrogen bond being on the same side of the substituting the methyl that we see in the middle, or on the other side, and so on. So it was a system for comparisons. Now, what can we say for the conformational preferences in vacuum? All populated conformers contain the hydrogen bond that we have just seen. And since it is there in all of them, we called it the first hydrogen bond. Then the orientation of the OH groups not engaged in hydrogen bonds has an influence. A non-negligible stabilization influence can go to, depending on which type of OH. The one at the bottom may have a difference of 1 kilocalorie per mole. The one at the top but not engaged in a hydrogen bond may have, like for example, if we go DRU, that is the last figure in the first row, we can see that this one can have an influence, can make a difference of 4 to 5 kilocalories per mole, whether it is downward or upward. So there are lots of details that influence the energy, the preferences. Then there are the CHO IHBs. These are weak hydrogen bonds, but they have non-negligible effect. We shall see some of them later. When there are additional OHO IHB that are possible, the conformational preferences are determined by their patterns. How many, usually the maximum possible number of hydrogen bonds. Again, when there are the hydrogen bonds OH pi, so pi can be a double bond like in a phenyl chain, can be a system if there is another phenyl group somewhere, they're also important. And when more than one acylphloroglucinol unit is present, there are 2 hydrogen bonds between the monomers, above and below the methylene bridge. Okay, here we can start seeing examples that we see that there are, these are the lowest energy conformers, and we can see that all of them have the hydrogen bond at the left, on the left, the first hydrogen bond. When the hydrogen bond is on the right, the energy is a bit higher, not much, but a bit higher. And then, of course, we can see, say, the one, this that I'm showing now, there is a phenyl group, so sometimes we have to consider also the possibility of a hydrogen bond between this OH and the phenyl group, and so on. There are all. Sesquiterate is the first one that we studied. As we can see, there are lots of possibilities there. Actually, these molecules have also given me, how to say, material for the education, because there are so many possibilities that one can show. So the first IHV, that is between the sp2O of the cell group and then a neighboring OH, an ortho OH, has a shorter length when it is on the right and when it is on the left. As classification, it is a moderate hydrogen bond bordering with a strong range, but is not strong. Is about 14, 15 kilocalories per mole. And then we have, of course, MP2. When there are experimental data, one can compare the length with experimental data, like we did for sesquiterate. Otherwise, we take MP2 results as a reference. And what we found is that HF results give longer length for the hydrogen bond, longer than experimental or than MP2, and DFT gives shorter ones. But we all know that HF underestimates the strength of a hydrogen bond, and DFT, at least the versions that, meaning with the functionals that we were using, tends to overestimate it. But that is also something interesting because we have a range within which the actual hydrogen bond length will lie. And we know roughly around the middle. Okay, here we can see hydrogen, acylphloroglucinous with the additional hydrogen bonds. And this is the one that I was showing earlier. No, here we have an additional OH in the R group. here as well, and they are making hydrogen bonds with the OH of the acylphloroglucinol moiety whenever they can. Sometimes we also get very interesting geometries. And the same happens if we have the donors or acceptors in R prime in the substituent in method to the acyl group. We can see this is the sesquiterbiated, the first molecule, and we can see a geometry. These are both low energy conformers. This is the lowest energy one, and we can see that the hydrogen bond is there. Of course, there is also the first hydrogen bond, but it is not shown here because the focus was on the additional ones. Now, what are the results in solution? In water solution, the delta G observation is negative. In acetonitrile is more often positive. In chloroform depends, but say the geometries in chloroform is very closer to the one in vacuum, what is normal because chloroform is non-polar. There can be important changes in water solution. The relative energies can change if the second hydrogen bond, the weaker hydrogen bonds break, and sometimes they break. It was interesting to find that even PCM sometimes shows that the polarizable continuum model sometimes manages to show that. Well, we usually think that PCM does not respond to the presence of possibility of hydrogen bonds with the solvent, but actually it does. But it does in a very indirect way, so we cannot take it as a complete information, but as an indication that maybe the one where this weaker hydrogen bond is opened is the lowest energy solution. Now, to check this better, we make adducts, that is complexes basically, but rather we complexes with explicit water molecules. So we add the water molecules and we see what happens. We can do, for example, for one water molecule in each position to see what is the interaction, the strength of the interaction between the molecule and or the given position and the one water molecule. Or we can try to make to approximate the first solvation layer. But that, of course, needs a bit of patience because molecules in these calculations, water molecules always show a tendency to stick to each other. So there is a need to change the input over and over until the molecule understands that we want it to bind, meaning the water molecules understand that we want them to bind to the central molecule. Here we can see some examples of water molecules approximating the first solvation layer, and we see that where there are other chains, it does not, meaning the water molecule will not go because these are not polar. But we can also see that the first hydrogen bond is an area that is hydrophobic. In most cases, water molecules keep away from it. Like here we have it on the left, and again, the water molecules keep away from it. Here we have a bit bigger molecules. Arsenol is an antioxidant molecule. And of course, even the ways of approximating the first solvation layer depends on the conformers and can have different number of molecules. Then here I just show the examples of the acylphloroglucinols with the specific biological activities. I prefer to do this through pictures because I think that putting tables requires a lot of time to read the tables. So it will not be interesting if I start reading numbers. Well, at least that was my perception. So this is CHPC, is the one that we have already seen, anti-tuberculosis and fungicide. Now, why is it important to study, for example, different molecular structure with anti-tuberculosis activity? We all know that there are strains of tuberculosis that now are resistant to all the antibiotics that have been used so far. So the only hopes that we have is new molecules that have the activity. And of course, molecules that come from natural sources are more, how to say, more prospective. We can have more hopes or more promising, because we already know that they go to the right place in the body, to the right protein, because we already know that the activity is exerted. So the main task can be improving on the structure to improve the activity, if possible. Then this is chinosine, and this is an anti-cancer. Euglobal is another anti-cancer. Myristinine is an anti-inflammatory. At the moment, I have a student who is doing a PhD on anti-cancer and anti-malaria together, because many compounds have both anti-malarial and anti-cancer activity. So we want to see if we find patterns. Okay, antioxidant acylphloroglucinols, they can be modeled by the ability to bind and reduce a copper ion. Then what happened is that when I submitted, for example, for hyperjovinol A, we shall see the structure soon, a reviewer said, why don't you try to see if it can join two molecules? A copper ion can bind two molecules if the activity will be better. So I tried that one as well, then verified that is it important that there are three OH, mutually meta OH, or if one of the OH goes, for example, so we have a simpler structure, the activity remains the same. And then for hyperjovinol A again, consider donor acceptor maps, when that was with a colleague in Mexico, so it was a collaboration. And the comparison of the reducing activity between two structures that are quite similar. These are the complexes of hyperjovinol A with the copper ion. This is the molecule itself, and then we can see, now, sorry, I should go back. It jumped. Here are the complexes, and I'm using both the monastic model and the space filling models, because I think the space filling model gives a better idea of how the ion nests itself inside the molecule. Okay, here is what I was mentioning when the two, one ion binds to two molecules, so we can see the poor ion being here. This has a much easier situation with lots of possibilities, but it turned out that the reducing ability does not increase. Okay, every now and then I have, okay, these are the molecules that were the 1,3 geranyl, okay, another molecule that differs from hyperjovinol only because it has a complete geranyl chain instead of having an OH in this position. And we can see that the ion prefers, the user preferences I should have mentioned even earlier, either between two oxygens when it finds a way, but not here. It could do it in the previous case. There should be one between two oxygens. Sorry, I forgot to put it. Or between an oxygen and a pi system, or just with the pi system when there are two of them. Like in this case, there are two double bonds and the ion is happily between them, binding to them. So that was also very interesting that the ion has this strong tendency to bind to pi systems. Here are other antioxidants, and the examples of the spin density maps, they tell us Now, what happens with these formation of complexes? One electron goes from the molecule to the ion. So the ion is reduced. The molecule remains with 1 ampere electron. And the spin density maps tell us where this ampere electron prefers to stay, not stay, but meaning to be around. And we can see that in most cases, it keeps away from the copper ion. I mean, it chooses areas of the molecule where that are not so close to the copper ion. Okay, now this is another one. How did we check the role of the 3 OH? By removing one at a time. So choosing, for example, this is a conformer with all the 3 OH, and then removing and seeing what happens with the complexes in the same position as for the full molecule. And the interaction, the reducing activity, how much the charge of copper is reduced, and the molecular interactions are better when all the 3 OH are there, even if they are far away from the binding site of the ion. Okay, then of course, sometimes one can have a bit of fun. There is this molecule that is quite interesting because it can make a sort of cycle. But then having these 2 COH group, acidic group in the 2 substituents, it makes dimers easily, and one could make chain. And then a colleague also suggested, why don't you make the ring dimers? And they come out. So these are just to see how many things one can do. Then from each of them, earlier or later, some ideas may come up. Now, for dimeric and trimeric acylphloroglucinols, we have to consider other, besides the orientation, the hydrogen bonds, and so on, there are other factors that influence the energy. One is the orientation of the mutual orientation of the units. And for trimeric acylphloroglucinols, also the mutual orientations of the methyl bridges. And I think it is easier to show. I forgot to take a watch, so I have no idea how I am with the time.
Are you still okay?
I'm still there.
Yeah, I'll let you know.
Okay, but I'm nearly there. But see, this is a dimeric acylphloroglucinol. And we can see that, for example, I should have put the images, but in this case, we have one acyl group up, one acyl group down. No, sorry, both of them up. We can also have one up and one down. And for each of them, we change the geometry of the monomers. So we end up with a number of possible conformers. And the problem is, why studying many conformers? Well, first of all, without studying all the realistically possible ones, we don't know which ones are the lowest energy ones. Second, having conformers that are higher energy shows the effect, by comparison, shows the effect of some of the factors. For example, a conformer where the second weaker hydrogen bond is removed will have a higher energy in vacuum. If we go to the precipitate now, if I don't lose it. Well, it could even be here, but I think precipitate is the most convenient for this. Sorry, I'm not managing to go up. Okay, if we go to this, for example, the lowest energy conformer have this second hydrogen bond besides having the first one, in this case as well. Now, there are conformers without the second hydrogen bonds. And if we are in vacuum, they have quite a higher energy than the ones with the hydrogen bonds. So we can know that this hydrogen bond has a good stabilizing effect, the weaker one. Of course, the first one has a bigger, stronger stabilizing effect, but even the weaker one has a comparable strong stabilizing effect. Now, when we use water solution, we find that the conformer without this bond becomes the lowest energy one. What is the reason? Because this donor, this OH and this oxygen, if this bond breaks, become available for intermolecular hydrogen bonds with water molecules. So that makes that conformer more comfortable, and so it becomes the one with lower energy. Now, this also shows the importance of calculations in solution, because if we consider only the situation in vacuum, we would consider this geometry as the one responsible for the biological activity. But if we consider in solution, it is the other one that is responsible. So when we try to understand, it is probably wise to take both into account. But we cannot neglect the one in solution, even if its energy in vacuum is comparatively high. Now, I think we were with the americ and trimeric. Sorry, it seems the computer is freezing, meaning it's feeling the cold of the weather. Okay. Now, this one is the second, is an antimalarial, has antimalarial properties. Now, we can see how many possibilities are there for a trimeric acylphloroglucinol, because we can have different mutual orientations of the monomers. In this case, for example, this one has the acyl group up, the second monomer has it down, and the third monomer has it down as well. But we can make all the possible combination of up and down. Then we have, here we have the methyl, the methylene group towards us, with the hydrogens towards us, and the other methylene group has the hydrogens towards the back. That means the structure is basically open, outstretched. If the two methylene bridges have the hydrogens towards the same side, the structure becomes, the conformer has the shape of a half bowl. So that becomes also quite interesting. For example, if we consider correlation effects, the half bowl shape has a greater correlation effects than the completely open shape. Now, cavity containing structures. That is it. I tried because I saw posters with the calixarines. That is big structures, ring-shaped, built from other hydroxybenzenes, usually the 1,2 or 1,3. Now, what is the advantage of cycloroglucinous if we want to make structures of this type? We have 3 linking levels, because one level will be the usual methylene bridge between the 2 units. But then we have a hydrogen bond above and a hydrogen bond below. We can also go back to the previous one. Yeah. And we can see Here we have, this is the methylene bridge. We have a hydrogen bond above, a hydrogen bond below. So if we consider making a ring or ring-shaped structure, tube-shaped structure, and so on, we have 3 levels of connections. The methylene bridge, 1 hydrogen bond on top, 1 at the bottom. So this gives a much more compact structure than the other hydroxybenzenes. And this is possible only with the 1,3,5 meaning hydroxybenzene, hydroxybenzene. So the result is that we have a greater cavity depth and tightly knitted walls. Of course, dispersion effects are important. And what was mentioned earlier, there are multi-units acylphloroglucinols that occur in nature. So they could be considered as precursors if one wants to make these ring-shaped things. The only problem is convincing the molecule to take the proper conformer. Okay, here are some examples. The first ones that I tried were the bowls with the 3, with 4, these are bowl shaped with the 4, and this is made of the fluoroglucinol, the parent compound. Here there is the aldehyde, meaning the first, the CRO is an aldehyde. Here it is with R equal methyl and so on. We can make it bigger and bigger. The same, we can make bowls with the 4 units. It will come, the next one should come. Okay, no, now it has skipped one. Yeah, it needs a bit of patience. Now, I wanted the one before this one. Okay, no, the bowls is okay. There are bowls with the other, with 5 and 6. That should be in the next slide. And it does not want to show. Sorry, please be patient. It is still. Nothing. It is not showing. Okay. The last figure here shows the bottom of, was showing the bottom of the bowls with the tube shape. Here was the bottom of the bowls. So we can see why it can make so tightly knitted bowls, because the OH at the bottom of the figure, as we showed it, will make hydrogen bonds among themselves. And another thing, of course, is that we have cooperative hydrogen bonds everywhere. Okay. For the tube, we have a different approach, because the bowl can be made with any type of, any number of units. And they must all be oriented in the same way. So at the bottom, there is a narrow part, and the larger part is in the higher upper ring. For the tubes, we need to have an even number of units and alternate the orientation. So one will be up, down, and then trying to convince them to make the tube. the first one and the last one to connect. So I've tried with the 4 and with the 6. And somebody said that these can be considered as a potential nanoparticles. But then it is the nanoparticle people who will know whether these are interesting or for what they can be interesting.
Prof, you have 5 minutes.
Okay, then I start. Well, but I think I will manage. Now, when we consider the dispersion correction, that is the Grimm dispersion correction, we see a change in the geometries. Well, it is very easy to see it in the tube shapes, the structure. A tube with the 4 units. This is without and with. And again, we have the structures with the space filling. This is a tube with the longer chain for the acyl group. And again, we can see that the distance decreases, even if it is not so strong as for this one, where we just have the methyl. Now, this is seen also with the trimeric acylphloroglucinols. I mentioned earlier that they have, if all the methylene bridges have the hydrogens on the same side, like here they have them towards us, then the conformer has a half-bow shape. And in this case, the effect is stronger than for the open conformer. There is also an effect on the open conformer because in any case, we have 3 benzene rings. That means they interact in some way. Even when they're not facing each other, they are still interacting because they are connected, basically. Okay, here is the last part, is the parent compound and its class. So we did a number of studies on the hydroxybenzene because it became fun to try to understand, and also because it helps understanding the results for the acylphloroglucinols. So we studied the conformational preferences, the behavior in water solution, and the adducts with the explicit water molecule and with the explicit acetonitrile molecule. Here are the 2 conformers. Here are some of the possible adducts with the explicit water molecules. One with the 4 oxygen near 1 OH because it likes that. Meaning the OH group likes having a square of oxygen when there is water around. We can see 1 oxygen is its own and 3 from water molecule. Or a possibility, a situation where it is has water all around. Okay, these are the adducts with explicit acetonitrile molecules. And this was another type of study that it was a collaboration with a colleague in Chile. He's a physicist and he studies magnetically induced current density. So decided that it was interesting to study the hydroxybenzenes. So we did it for all the hydroxybenzenes. Okay, I should go to. It seems no. So how do I get back? No. Because whichever way I move this thing of the mouse, it does. Sorry, I'm trying to go back a moment. I will try to do it fast, but I don't know what is happening.
You can go back to presentation.
Going back to that.
Yeah, that one.
Okay, now going to the last. No, I don't need to go through all the story, but maybe it is the fastest thing. Probably that it does not move fast. I don't know if there is any way of moving it fast. But in any case, I can I can also talk about the conclusions while we wait to get the slides, because we have seen that basically a whole class of compounds gives a big class. This class has stopped. The share window is closed. How did it close?
You can just reshare. That's fine.
Yeah, but I must find a way of getting. Okay, this one. I should get okay, here, the option. Well, I had to tell it, okay, because otherwise it will not. Chatter, hide, no. Share screen, okay. But now where do I find it? It seems it has disappeared.
Maybe you close the presentation. You might need to reopen it then if that's the case.
Okay, I will try to open because I wanted to show a couple, just 2 slides at them. Oh, then. But now
I have the slides on my side. If I can share from my side, I can
yeah, if you can go to conclusions, I think your computer will be faster than mine.
Let me see what I see on my side.
Yeah, okay, so we'll try and share it from here, then you can just speak through it. I think that would be better.
Let's just see what I can see on my side.
Well, meanwhile, I also try to find mine. Exit full screen. Now I should be able to find it.
It's a problem on my side as well, Krishna, on my laptop, so I cannot share.
Probably the file is too big because of all those structures. Okay, I found it, and now I should go back. How do I go back to the presentation? To the...
just click on the Zoom. There should be a Zoom thing there somewhere.
No, I found it. Now I just have to share the screen share. Let us see what happens. It is there. And okay, I should use this one.
No, wait. You can maybe escape from that. You can go to your last slide. So just press escape.
Escape?
Yeah. And there on the left,
no, it does not go.
Bar. No. You see on the left-hand side? Go to your left. Yeah.
Oh, okay. Down. Sorry.
Yeah.
I was thinking then it is just faster simply to scroll and go to the slide.
That's right. Yeah. Just click on the slide that you want.
Yeah, but I must wait until they wake up.
Well, if you click on it, it will refresh that slide the quickest. So click on the one you want. It should hopefully refresh that quickly.
No, PowerPoint is not responding.
Leave it. It's coming.
It takes time.
It takes time, yes.
Okay, but we were here. So the parent compound. So I think we were on the next slide from this one. And we can see that we had a high variety of research questions of interest focuses. Actually, we are not yet finished. There are still lots of things that can be done with this same compound. They are not the only compounds that I'm studying, but this is the biggest class. So in current in progress, there is the study of anti-malaria, anti-cancer, acylphloroglucinol, and other possible cavity-containing structure. And of course, I want to recall that it is doing all these nice things. The crucial role is that we can use the CHPC resources. Otherwise, it would take probably what can be done in a few months would require 2, 3, 4 years, or even more, if one had to do, and even more because it is very difficult to make a certain work certain jobs on desktop computers or other kind of resources. I mean, the CHPC allows the possibility of doing a lot of work. And now, if I may, so I must ask permission first, but I would like to invite to contribute. The deadline of 31st July is to give the title and the abstract. If anybody is interested in calculation in solution, is a special issue. And of course, this is an MDPI, so we all know they're very expensive. As a publication fee, they're open access. But they also give a 30% discount for special issues. But of course, so if somebody is interested in solutions. Thank you. Thank you. Thank you, the CHPC, for the invitation. And thank all the people who have joined that I'm not being able to see because I was looking at the slides. But I hope it has been somehow interesting.
Yes, thank you very much, Prof. So guys, if you want to ask questions, you can just post your questions in the chat, or you can maybe raise a hand. We're going to, obviously, due to the technical difficulties, we're going to have to go a little bit over just for the question part. But I see there is a question in the chat by Tisome. He asks, have you done any corrections for basis set superposition error during the interaction energy calculation?
Depending on the kind of study. I mean, if the interaction is strong, it is not needed. Like, for example, if we consider the interaction between a molecule and an ion, it is not needed because the interaction is very strong. It's 300 of the order of 300 or 300 plus kilocalories per mole. I did it when studying the adducts with explicit water molecules or explicit acetonitrile molecules, or any place where there are interactions that are not strong, because that is when the error, the basis set superposition error, becomes relevant, is not negligible. While for very strong interaction, it can be considered negligible.
Okay, so while we're waiting on other questions, I've got one from my side is, have you considered using the Minnesota functionals instead of B3 for your stuff?
Sorry?
The Minnesota functionals, the MO models, as opposed to B3.
No, okay, I tried it for other molecules. I tried it for other molecules, not for this class, because the other molecules where I tried were new. I did not have the problem of comparing with the lots of previous results. Well, in this case, there is the problem of comparing. So what I'm doing now is doing the study with the B3 lip and the B3 lip D3, with the Grimer correction, because then I can, and that actually is also, at least for me, is quite interesting because it shows how much the dispersion influence and in which cases it is more important, in which cases it is less important. What I showed when I said the dispersion, the effect of dispersion corrections.
Yeah. Okay, so there's one more from my side though. I would like to know, so I see with your explicit water molecules, you'll kind of randomly place the waters, say in the first solvation sphere. Have you maybe tried looking at perhaps putting it in a water box using molecular mechanics and then taking just those waters that sit within that first solvation sphere and running a QM on that?
Okay, that is one of the things that would be interesting for the future. Why do these water molecules, as they are put for these molecules, they are not actually very random when I prepare the input, because there are specific hydrogen bond donor and acceptors. So one utilizes those sites because it is clear that the water molecule will bind to those sites, first of all. Then the others will join. But first of all, they will try to bind to the sites that are donor or acceptor. Actually, the water molecule prefers to be acceptor than donor. meaning acceptor to the OH, the phenyl OH, than donor to the oxygen. The interaction is stronger when the phenyl OH is a donor. But say they're built, those are built considering the hydrogen bonds.
Okay.
And I think that is also interesting because these are interactions that are, how to say, they're perceived, if we want, or taken into account better by quantum mechanic approaches.
No, okay, that I'm fine with that. I don't see any other questions. So with that, we'd like to thank you, Prof, for the good presentation. I'm sure everybody enjoyed it. And yes, thank you everyone for joining the session. We will end it here. Okay.
And thank you again.
Thank you very much, Professor Liliana. We appreciate the time taken to participate in this webinar and to present.
Well, I really enjoyed it.
I
enjoy when I can talk about molecules. It is a way of playing. Well, I would not say playing, but sometimes. But thank you.
Yeah, so thank you. We have, of course, recorded this, and it becomes part of our let's call it our archive of videos that we keep available. So if anybody in future wants to look at this, you are welcome to direct them. So I think Benjamin did put it there in the chat box also, where the YouTube link is.
Oh, so you will send me the link that I can give to anybody.
Yeah. You can see it there in the chat box also. So yeah, even if you want on your side to send to people, say, a recording of the presentation, you can just give that link to them and they will be able to see it.
I think it is the same as for the other presentations that we can access.
Yes.
Okay.
So you can just go and select which one you want to do. Okay. But thank you very much. We appreciate it.
Thank you.
With that, we can probably then close this session. Enjoy the rest of your day.
You too. Thank you.
Thanks, Krishna.
All right, thank you.
Bye-bye.